Everyone, welcome to the channel. So in this video, we're going to talk about the distortion in recorded satellite images. So in this video, we're going to focus on distortion in the recorded images. So images are never perfect when recorded, and it is the purpose of this video and those which follows to understand that an image is acquired by a remote sensing machine contains errors compared with the regions on the ground being imaged. We are familiar with an image error in our day-to-day life. So when we take photos with a handheld cameras, we often encounter distortions because the subject or the camera has moved, or because the sunlight glints in from the side, or because the contrast and the brightness of the images are poor compared with the reality. Exactly the same is true with the images recorded by the satellite sensors. Before we can make the sensible use of those images, we need to understand the source of the error and the distortion, and the means by which we can correct them to create an image which is as close to the actual landscape as possible. In this video, we will concentrate on the most important types of distortion that frequently occur in the remote sensing imagery, and often they are corrected before the images are sold to the users, and in your work you may not be particularly aware of them. Nevertheless, it is important that we understand how a distortion arises and the means by which they are corrected. In some cases, the most notably when images are recorded using an aircraft and drone platforms, you may have no other alternative than to correct the errors yourself. And an important reason for understanding the correction of the distortion in the image geometry is that the technique we employ for the correction can also be used to register an images to the maps and the images to other images. Finally, as with any computer processing in image analysis and remote sensing, if you understand the basis of this algorithm employed, you are in a much better position to understand their limitation and their characteristics. Distortions can occur in the geometry of an image and in its brightness. We will look at each of those in turn, commencing with brightness distortions. Distortions in brightness are generally known as radiometric distortions. The radiometry, you will recall, which describes the brightness level in an image. And now you can see from this particular slide here, the major source of radiometric distortions are subdivided into three subcategories: those caused by the presence of those caused by the persons of the instrument themselves, and those caused by the shape of the solar radiation curve, that is the Planck radiation graph for solar radiation, which we have shown in our previous video. And finally, those caused by the effect of the atmosphere, and particularly how the effect of the atmosphere varies with wavelength. Any radiometric characteristics that are wavelength dependent or cause a relative brightness distortion among the bands. That is a critical concern because the band to band relative brightness difference are what allows us to understand the spectral reflectance characteristics of the Earth's surface types. Recall the difference between the spectral reflectance curve for vegetation, soil and water from our previous video. We don't want those relativities upset by radiometric distortions. So let's start by looking at the effect of instrumentation errors on brightness. We are particularly interested in the behavior of the radiation detectors that measures the upwelling energy in each band. So as you can see on the bottom left hand side of the slide here, the ideal radiation detectors has a linear characteristics that indicates the magnitude of the electrical signal generated by a certain level of incident radiation. Ideally, the curve has to be linear so that the variation of the output signal mirrors those of the input signal, that is of the input radiation level. There are two important detector properties described in this graph. The first is the slope, which is referred to as the gain of the detectors. A higher gain detector will generate a larger electrical signal for a given input level of radiation. The second property is the offset, which indicates the detector will generate a very small signal even if there is no radiation input. That is just a characteristics of electrical devices, that is is sometimes called as a dark current. It can be reduced by cooling the detectors. If a particular imaging sensor consists of a number of detectors such as the ETM plus and the HRV family, it is important that they gain and the offsets be matched as closely as possible. In practice, however, the situation is more like that shown on the bottom right hand side of this graph here, this particular graph. Although the drawing is exaggerated, the detectors will often have a slight variation in their offsets and a slight difference in their gains. In the simple case of the Landsat multispectral scanner, there are 6 detectors per band. If there are a noticeable difference in gain and offsets, it is possible to see it's dropping in an image which repeats every 6 lines. So this slide gives us an example of the land stripping in the Landsat multispectral scanner image. So you can able to view from this image here. So here you can able to visualize the line striping here. So in this particular original image, this is the original image. So again you can able to see there is a line stripping in this image here, and versus this image is a corrected one. So you can able to visualize the line stripping has been removed in this particular image. So you can able to compare the difference. So yeah, you can able to see the line stripping here. So the line stripping resulting from the detector's mismatch, you will see that the line stripping is very noticeable in the water part of the image. How can we reduce the line striping distortions caused by a mismatch in the sensor characteristics? A simple method is to compute the histograms of the signals recorded by each individual detectors and then match means and the standard deviation of those histograms. And we will not go in details here, but it is a fairly simple process and often employed in practice when we get to the image contrast modification. In our upcoming videos, you will be able to see how this is done. When that procedure is applied, the corrected images on the bottom of the, that is in the left side of the slide results, you will see that the line striping has been reduced considerably compared to the original image. So next we examine the variation with the wavelength of the solar radiation curve. So this is our solar radiation curve. You can able to see here in the top left side of the slide here. As seen here, over the optical range of wavelengths, there can be a significant change in the level of radiation falling on the Earth's surface. That could suggest that the visible wavelength could appear brighter than those in the infrared range just because of the level of the sunlight and not because of the spectral reflectance variation of a given cover type. So from the graph here, you can able to visualize here the y-axis here represents the incident sunlight and the x-axis here represents the wavelength. So in the wavelength we have ultraviolet, visible and reflective infrared, and typically you can able to observe there is a significant variation in the level of solar radiation in this particular visible range compared with the reflective and infrared and ultraviolet range. Clearly, the solar radiation needs to be corrected if a meaningful spectral reflectance information is to be obtained in a recorded image. The correction can be carried out by using the ideal Planck curve for broadband sensors and for hyperspectral instrument, however, in which the spectral resolution is very high. The actual solar curve measured above the Earth's atmosphere needs to be used because the real solar spectrum contains fine spectral details, notably Fraunhofer lines. And now let us look at the effects of the atmosphere on the brightness of an image. The atmosphere absorbs the radiation on its path from the sun to the pixel and from pixel to the sensor. So you can able to see from here the incident sunlight here, which gets reflected from the Earth's surface and get reflected from the Earth's surface to the energy to the sensor. But you can able to see from this image the atmosphere also scatters the radiation directly into the sensors. You can able to see from here the incident radiation gets scattered in the atmosphere, which is directed towards the sensor. There is a third more subtle effect, and there is a scattering from the atmosphere onto the pixel via diffuse, not a direct path, also shown here. You can able to see from here. So you can able to see the diffuse scattering by the atmosphere onto the pixel. There are other less obvious scattering pathways as well, all of which needs to be considered when looking at the effects of the atmosphere on the recorded image data. To make the situation simpler, consider just two mechanisms shown here. We know that the direct path from the sun to the pixel and the pixel to the sensor suffers a selective absorption. But what does atmospheric scattering pathway do to the recorded signals? So the answer to that question is quite complex, and that depends on the size of the particles that make up the particular atmosphere through which the imaging take place. So here from the image we have shown three different atmospheres. So at the bottom here you can able to see that we have a clear atmosphere in which the only scattering elements are the molecules of the gases that makes up the atmosphere itself. And now in the middle the atmosphere also contains some smaller particulates such as a mist. Now at the top here the atmosphere is foggy, so you can able to compare the image at different atmospheric condition. Here you can able to see here. So here the hills are only partially visible, here the hills are completely not visible here. So at the top here the atmosphere is foggy, containing a large scattering particles of water. Scattering from a clear atmosphere is called Rayleigh scattering. It is a strongly wavelength dependent, as we have shown from the graph here. You can able to see here. So with the blue light from the graph here, you can able to observe that with the blue light being scattered the most here, you can able to see here. So the net effect is blue coloring. You can able to see the atmosphere in blue color, and that is why we see the sky as blue on a clear day. So you can also go through from this definition. When a sky is clear, it is only the blue end of the spectrum that is affected. The short wavelength of blue light is scattering by atmospheric gas. It is called the Rayleigh scattering. And now let me get to this second graph here. The scattering from the light haze is called as Mia scattering. That is Mie scattering. It is not as strongly depend on wavelength as Rayleigh scattering. So the effect is bluish white appearance. So you can able to see from here, and also the reflect in the curve here, which indicates a bluish white appearance. And now in the last in this graph here, the scattering by the large particulates is almost independent of wavelength, so that the atmosphere then appears almost white here. You can able to see from this image, it appears to be a white, and that is why we see the fog as a white. These scattered signal superimposes on the direct path signal. As you might expect, the short wavelengths are affected more than the long wavelengths. One simple mean for compensating the wavelength dependent effect of the atmospheric scattering is to produce a histogram of each of the recorded image bands. The effects of the atmospheric scattering shown up in the histogram as offset from 0. So you can able to see from here, this is an effect of atmospheric scattering, which is indicated in the dotted line here. Recall that the shorter wavelengths are affected more. This is seen and visible blue histogram in this example here. You can able to see from here, this is our visible blue histogram. As the wavelength increases, the offset chooses an atmospheric scattering reduces as given in the figure here. So you can able to see in the visible blue here, this offset is subtracted from the brightness of all pixel in the blue band. So let me repeat this one more time. As the wavelength increases, the offset atmospheric scattering gets reduced, as you can able to see from this image here. From visible to mid infrared, you can able to see the offset has reduced. In order to correct for the effect of an atmosphere, the offsets are subtracted in each case, so that the image histogram are reset to the start from 0. In fact, the offsets are subtracted from the brightness of the every pixel in the image, which leads to the corrected histogram. Correcting for the effects of atmospheric absorption on direct path signal usually requires a knowledge of wave dependence of the various actual observers in the atmosphere. There are a number of quite comprehensive software packages that can be used for the task. This slide is an illustration of the effects of all atmospheric constitutes on the spectrum of vegetation pixel at the top. It also includes the distortion caused by the shape of the solid radiation curve. The corrected version is at the bottom here. You can able to see that. Note that a complete absorption due to water vapor cannot be compensated, but that is not a problem because there is usually no significant information available in any case in those regions. So the key points that is covered in this video. So when images are recorded, they invariably contains a distortion which must be corrected. The distortion in the recorded brightness values are called a radiometric distortion. Can result from sensor non-idealities, the wavelength variation in the solar radiation, and the absorbing and the scattering behavior of the atmospheric path of the energy to and from a pixel. When several detectors are used to record an image in a particular waveband, mismatches in their input-output characteristics can lead to a transversive or a longitudinal line stripping. The wavelength dependence of the solar energy incident on the Earth's surface is described by a Planck's radiation law. The dependence is particularly strong from the visible to the reflected infrared region. As seen in the previous video, the atmospheric gases have absorption features at a specific wavelength. They will superimpose themselves on spectrum of the ground cover type being imaged. And last, the atmospheric scattering adds to the signal recorded by the sensor and should be removed. So in this video I have shown you the distortion in the recorded satellite images, and please stay tuned for the upcoming videos that is related to the remote sensing tutorial series. So thanks for watching, and please like and subscribe to our channel, and follow us on our social platforms just given in our channel description. So thanks for watching.